Hello, we are going to study how to draw the ILD of indeterminate continuous beams, especially for shear force and bending moment at z distance. So let me take a similar example or same example, and we'll see how to find the ILD for shear force and bending moment. First we'll find out ILD for shear force, and then we'll find the ILD for the bending moment. So problem will be asked something like this: draw ILD for shear force and bending moment at let us say midpoint of span AB. Let us, same way we will take an interval of 1 meter, that is we have to take spacing of 1 meter. So let us first focus on ILD for shear force. ILD for shear force. Okay, so what is the problem given? So we have 5 meter span and 4 meter span. This is 5 meter and this is 4 meter. It is asked to take an interval of 1 meter. So from here, if we start 1, 2, 3, 4 and 5. So 1 meter, 2 meter, 3 meter, 4 meter and 5 meter. And it is also asked to find the this thing shear force at center, that is mid span. So let us consider this as a center. So your Z value becomes mid of 5, that is 5 by 2, 2.5. okay, so this is the given problem. So we will go step by step. As you know, first step is to find out ILD of determinate beam. So how will you make determinate? By making providing hinge here, this beam becomes a determinate beam, and then you can, let me take little bigger so that you can see it clearly. So again we have to break it at 2.5, that is half. Okay, so then you can see the ILD will come something like this, as hinge is here, so it will be like a determinate ILD. And you know Z by L, so you know Z is half, that is Z is equal to 2.5, and that is 2.5 by 5 is equal to how much it will come? 0.5. This will be 0.5. And similarly here 1 minus Z by L, that is again 0.5. okay, so once you have this determinate ILD, you have to divide it by EI. So we will divide it by EI. So 0.5 by EI, this side also it is 0.5 by EI. Now we will mark once again intervals: 1 meter, 2 meter, this is 2.5, 3 meter, 4 meter. okay, and then we have to find out these ordinates. okay, so how to find out? Like for 2.5 it is 0.5, then for 2 meter how much it is from this side, for 1 meter how much. So this is at 1 meter, this is at 2 meter from this side, this is at 1 meter and this is at 2 meter. So if it is for 0.5 it is at 2.5, then for 2 it will be how much? So if you do that, so you will get this as a 0.4. so if you can see, this will come as a 0.4 by L, this will come as a 0.2 by L. Similarly from this side, if you do, this will come as, sorry, not by L, by EI, we have to divide by EI. So 0.4 by EI, and this value come as a 0.2 by EI. So that's how it will come. So 0.4 by EI, 0.2 by EI, and this side it will have like an interval of 1 meter, 1, 2, 3 and 4. So that way you have interval. So but there is a no value here because as it is a hinge, it is not going ahead. So this is step 1. So let us go to step 2. What step 2 suggests is we have to find out, because of this determinate 0.5 by EIL, 0.5 by EI, how much fixed end movement generates, and because of that what will be the end movement. So you will have to once again I will draw this diagram quickly. Okay, so what you'll have to do is you have to continue this by dotted, and this will be like 1 by EI. Okay, and this, if you continue this side also, it will be again 1 by EI. Okay, and using this principle you'll have to first find out, this is A, B and C. So using this principle you'll have to find out theta A, and this will be theta B. And you can see in case of rotation, in case of movement, if it is going anti-clockwise negative and clockwise positive, but in case of rotation it is opposite. If it is going anti-clockwise, if it is going anti-clockwise, then it will be a kind of if it is going anti-clockwise it will be positive, and if it is going clockwise it will be negative. So both, you can see this theta A and theta B both are going clockwise, that's why they will be negative. And as it is at the it has the final 1 by EL and 1 by EL, so both theta A and theta B are same. So theta A is equal to theta B is equal to minus 1 by EI. You can apply the kind of tan theta formula. Minus 1 by EI is the front side, and then this will be by L. So this will come as a minus 1 by EI, and let us put L value as a 5. Okay, so this is theta A and theta B. And then similar to our stiffness method end movement formula, we can apply what is stiffness method formula. So that is FEM plus 2 EI by L in bracket 2 theta A plus theta B. Same in this case, FEM is not there, so directly we are starting. FEM AB will be 2 EI by L, 2 EI by L in bracket 2 theta A plus theta B. Okay, so let us put 2 EI by 5. Okay, L is 5 in bracket, both are minus, so minus 2 by 5 EI minus 1 by 5 EI. And if you do this, so it will come as a minus 0.24. Similarly, FEM BA will also come same, because both the thetas are same. FEM BA will also be 2 EI by L, that is 5 in bracket minus 2 theta B, that is 2 by 5 EI minus theta A, that is minus 1 by EI, and that way you will get as a minus 0.24. Okay, so once you have FEM AB and FEM BA, we will find out distribution factor and apply the moment distribution method. So what will be distribution factor? DFBA will be nothing but 3 EI by L, that is 5, divided by 3 EI by L, that is 5, 3 EI by 5, and then 3 EI by L, the other span is 4, and if you do this is 0.44, and DFBC will be how much? DFBC is 1 minus 0.44 is equal to 0.54. Already we had calculated, so I am going fast. So now we will apply moment distribution method. So this side distribution factor is 0.44, this side it is 0.5. How much is? Both the fixed end moments are same, that is minus 0.24, minus 0.24. So we will substitute minus 0.24, minus 0.24. So this is AB, this is BA, this is BC, this is CB. Okay, so this is 0 and this is 0. And now how will you this is 1 and this is 1. So how will you get, so as this is hinged support, it will release completely. Here if you distribute, it will come as a plus 0.106, that is positive 0.24 you will have to balance, multiplied by 0.4 you will get this, and then plus 134, and then you have to do carry over. This is balancing step, then carry over. So if you do carry over, it comes as a 0.12, and then this 0.12 has to be balanced, multiplied by 0.4, that will come as a minus 0.53 minus 0.067, and that's it, balance took place. And then if you add, this will be 0 0, and here it comes as a minus 0.067, this comes as a 0.067. Now whether this is creating, this is nothing but our kml square by EI, we have to get the indeterminate displacement, and so this is the value, that is 0.067 is a movement. But whether it is creating positive effect or negative effect, how to do that? So where movement is applied, you should see this is negative, means it should go to anti-clockwise. So you can show the anti-clockwise arrow this way, this is going clockwise, so this show this as a clockwise value. So what this arrow is doing, so this is pushing the beam downward. What this arrow is doing, this is pushing this beam downward, so it will create minus. So moment displacement, indeterminate displacement will become minus kml square by EI. Indeterminate displacement will become minus kml square by EI, where m is this, what is k? So you'll have to get k by putting n values. N is equal to 1 here and n is equal to 0 here. In this case, n is equal to 0 here. So if you see here, you have to go by 1 meter interval. So there are 5 divisions, so it will become 0.2 interval. So this will become 0.8, 0.6, 0.4 and 0.2. And then we have to take one value at the center also, that is at the midpoint, and of course that value is nothing but 0.5. So you'll have to find out k values for these n's. So similarly this side 1 meter interval is the total distance is 4 meters. So 1 meter interval, if you take 4 interval will be there, so that's why 0.25 interval is there, 0.75, 1.75, 0.5 and 0.25 and 0. So these are the n values, and if you know the how to get for the given n, how to get the k value. So n is equal to 0, so sorry, we'll start from this side. N is equal to 0, then k is equal to n minus n cube by 6, as n 0, so this will k will be 0. So n is equal to 0.2, so k will become 0.2 minus 0.2 cube by 6, and then it will come out as a 0.032. Likewise you can quickly do for all the k values. So by 6, this will come out as a 0.056. Then we have to get n is equal to 0.5, k is equal to 0.5 minus 0.5 cube by 6. This comes out to be 0.0625. n is equal to 0.6, k is equal to 0.6 minus 0.6 cube by 6, 0.064. n is equal to 0.8, k is equal to 0.8 minus 0.8 cube by 6, and this comes out to be 0.048, and n is equal to 1, k is equal to 1 minus 1 cube by 6, that is 0. So likewise the other side also you will have to get the n values. So n's are 0.75, 0.5 and 25 this side. n is equal to 0.75, k is equal to 0.75 minus 0.75 cube by 6 is equal to 0.0546, n is equal to 0.5, it is k is equal to 0.5 minus 0.5 cube by 6, and this comes out to be 0.0625. n is equal to 0.25, k is equal to 0.25 minus 0.25 cube by 6, k is equal to 0.039, and n is equal to 0, k is equal to 0. So once we have n versus k value, we can go to the final indeterminate displacement. How will you get those final indeterminate displacement? That we can get it from the formula, that is, what is total displacement? Y is equal to EI in bracket determinate displacement plus or minus, in this case, so plus indeterminate displacement. Okay, in this case what has happened, indeterminate displacement has come out as a, from this case we can note this, this has gone down, that's why minus. K value we know 0.6, which we got by moment distribution. L we know, and that we k values we have got from each of the n, and determinate displacements are this one, so that is coming from the ILD of determinate divided by EI. So if you start from this diagram, so we can get here. So this is determinate displacement here, let us call this as a first point as a y0. So EI into determinate displacement here is 0, and minus kml square, k is in this case 0, m is 0.067, and el is 5 square divided by EI is equal to 0 only, y0 will be 0. Then comes y1, so y1 is equal to, you can see here it is minus 0.2 by EI into minus 0.2 by EI minus k. In this case k will be, for n is equal to from this side 0.2, it is 0.032 by 0.032 into 0.067 into 5 square by EI, and this comes out to be minus 0.2536. okay, minus 0.2536. Similarly you can get all other values. Y to EI is equal to EI in bracket, so in this case second value is that is minus 0.4 by EI minus how much, 0, k is 0.056 into m is 0.067, 5 square by EI, and this value comes out to be minus 0.49. Similarly we will get y3 EI in bracket, what is y3 is not there, so this is, we have two values, we will call it as a yc1 and yc2. These are the center points, so we will call it maybe yc1. yc1 is what, this is 0.5 by EI minus 0.5 by EI minus for n is equal to 0.5, what is k, it is 0.0625 into 0.067 into 5 square divided by EI, and then this comes out to be minus 0.605. So similarly yc2, that is now it has gone from negative to positive, so please see the difference. Negative, at one point there will be two values, so it will be EI in bracket, instead of minus 0.5 it will become now plus 0.5 by EI. The remaining part will remain same because it is at the same location, minus 0.625 into 0.067 into 5 square divided by EI, and this value comes out to be plus 0.395. Now we'll go to this point, that is 0.4 by EI, so we will call it as a y3 EI into bracket 0.4 by EI minus from this side it is, now it has become n as a 1.8.6. for n is equal to 0.6, what is value of k, this will come out as a minus 0.064 into 0.067 into, now span we have to be very careful in this case also, again 5 square divided by EI, and this comes out to be 0.292. Similarly, y4 is equal to EI into bracket 0.2 by EI. So you can note determinate displacement here, 0.2 by EI positive minus 0.048 into 0.067 into 5 square divided by EI, and this value comes out to be plus 119. And then at the center you can see determinate displacement is 0, k is 0, so y5 is equal to EI into 0 plus 0, that 0 minus 0 you can say, it will come out as 0. Then we will have y6, y7, y8 and y9. You can see y6, y7, y8, y9 determinate displacement is 0, so I will not show again and again here. Directly we will have only indeterminate displacement, that is minus kml square in this case, so it will be negative. So y6 is equal to, you have EI in bracket 0 minus 0.546 into 0.067 into 4 square by EI is equal to minus 0.0585. y7 is equal to EI in bracket 0 minus 0.0625 into 0.067 into 4 square divided by. So this problem is very important because usually in case of bridge design etc., we need ILD for shear force and bending moment at various critical locations. So that's why, as compared to ILD of reactions, usually we have to we should ensure that we know how to calculate ILD of shear force and bending moment diagram. So this comes out to be minus 0.0418, and this last y9 is equal to, it will be EI 0 minus 0, that is 0. So now we got from directly y0 to various values up to y9, and then how to draw ILD of this. So let me take this fresh page and let me draw ILD in a little bigger form so that it will be easy. So if you can see here, this was 1, 2, 3, 4 and 5, we can say, up to this is center 5. Then thereafter 4 interval 1, 2, 3 and 4. So our beam is up to this part you can ignore. So you can call it as y0, y1, y2, and then at the center 2.5 we have yc1 and yc2, y3, y4, y5, y6, y7, y8 and y9. Okay, so you can see it. You can first draw the diagram of determinate so that we can understand the trend. So it is diagram of determinate, and you can see the first part, what has happened, negative and negative summation has become negative addition. So that means the determinate value when it was 0.2, in total indeterminate value has become 0.25. So it means increase. So this curve will come as a convex type. So this curve will come something like this. Okay, and then this will go here. Okay, and now you can see in the positive part, that is after y5, so I'm sorry, so after this yc2, it has started becoming in the, when there is a positive 0.5 value, it has become subtracted. When there is a positive 0.5, total value has come 395. When it was 0.4 determinate, it has become 292. That means it has, as compared to determinate, it has, the values have started decreasing. So that means you will have to draw the curve in the convex type. You will have to draw the curve in the convex type, and thereafter this convex part has continued like this. You can note my hand curve. So this is very important, very simple. It is obviously that smooth curve should continue in the where there is a no shear force part in case of determinate case. So this way it will come out, and now simply you will have to mark these points and put the values. So that's it. So quickly I will write here 0.2536, this will be 0.49, and this will be 605, this will be 0.395. You can note here again it has followed the rule of ILD, that is 395 plus 605, it has addition will come as a 1. So then 0.292, then 0.119 and 0, and this side it will be negative 0.58, 0.585, 0.067 and 0.0418. So that's it. So this is the ILD for shear force at Z. Z was in this case 2.5, that is half of the 5 meter span. Okay, so quickly let me go to the next continued problem in this case, that is the problem of ILD for bending moment. So part B in this case, that is ILD of bending moment at Z. Again here Z is 2.5 from A, that is mid span of AB. So let me draw this diagram again. So let us say 1 meter, 2 meter, 3 meter, 4 meter and 5 meter. So this is A and B. Okay, and then thereafter again 1 meter, 2 meter, 3 meter and 4 meter. So this is C. Okay, and then out of this at the center, that is 2.5 it is said. So if you draw the determinate value, it will come out something like this. And you know that is how to get the determinate ILD by providing hinge here. So it is nothing but you can say A into B by L. So this value will be AB by L. So this side it is 2.5 into 2.5 divided by 5. So it will come out as a 1.25 and then divided by EI, Okay, so once you have this value, you have to find out these values at these intervals again. Okay, so these intervals also. So how to find out? So you can note here for 2.5 it is 1.25. Then what is it for 2 meter and what is it for 1 meter? From this side also it is 2 meter and this is also 1 meter. So how to get that? So you'll have to divide 1.25 by 2.5 and multiply once by 2, once by 1, and then you will see that this will come as a 1 by EI and this will come as a 0.5 by EI. This will come as a 0.5 by. Similarly this side also it will be 1 by EI and this will come as a 0.5 by EI, and this side there is a no determinate ILD. Now this is our step 1, that is we have to get determinate displacement. How to get determinate displacement? So we draw the ILD of determinate and divide it by EI. What is step 2? Because of this determinate displacement, how much it has created moment. So how to get that? As I told you in the previous example, if this is the rotation is clockwise, it will create negative, it is opposite of moment. If rotation is creating clockwise, then it will create negative. If it is anti-clockwise, it will create positive. So that way if you take this will be theta A and this is theta B, then theta A will become as a, it will be like a opposite of that. So it will be B by EIL, and you will see that this is going anti-clockwise, so that's why it is positive. So it will be 2.5 by EI by 5, so that will come as a 0.5 by EI, whereas theta B will come negative because it is going clockwise, so it will be minus, as A and B are same here, so answer will come same. But if A and B are not same, you will have to be you have to use, in case of A, B by EIL, in case of B it will be A by EIL. Okay, so you can see here it will come out as a minus 2.5 by EI into 5 is equal to minus 0.5 by EI. And as you know, theta A and theta B, we can find out FEMAB and FEMBA using MAB and MBA formula. So FEMAB will be equal to how much? It will be 2 EI by L in bracket 2 theta A plus theta B. So if you put 2 EI, L is 5, in bracket 2 into theta A is 0.5 by EI, minus this will be 0.5 by EI, and this FEMAB will come out as 0.2. This will come out as a 0.2, like you can note here, this will be 1 minus 0.51, and that is positive 0.2 by 5 is positive. Something wrong here. So 2 by 5 is how much? 0.4, I guess. So sorry, this is 0.4, and similarly FEMBA will be 2 by EIL, that is 2 by EIL into 2 theta B plus theta A, and this comes out to be like 2 EI by 5 in bracket, it will be 2 into minus 0.5 divided by EI in plus 0.5 by EI, and then you can see this is minus 1 and this will be minus 1, I'm sorry, here 1 minus 0.5 was 0.5, so it was multiplied by 0.5, this will be 0.2 only. Okay, correct. And this similarly here also 2 into minus 0.5 will become as a minus 1, and then plus 0.5, this will come as a minus 0.5, and 2 by 5 is 0.4 into this will be come out as a minus 0.2. Okay, so these are FEMAB and FEMBA, and as you know the span is same. We have already calculated distribution factors. Let me show you and continue to save time. So we have calculated distribution factors. So distribution factors for span 5 meter and 4 meter, 2EI by 3EI by 5 by divided by 3i by 5 plus 3i by 5, that will be 0.4, and 1 minus 0.4 is 0.55. So once you know distribution factor, once you know fixed end moment, so we can apply the moment distribution method. So we have FEM as for we will write span also AB, BA, BC and CB. So this both moments are 0 here, and here FEMAB is 0.2 and FEMBA is minus 0.2, and if you start balancing here, this will come as a minus 0.2 and this will come as a point, so minus 0.2 will be balanced by plus 0.2, so multiply by 0.44, it will come as a 0.088 and 0.112 and 0, and then you do carry over. If you do carry over, it will come as a minus 0.1. Again, if you balance this minus 0.1, positive balancing will be there, 0.044 and 0.056. If you add this together, this will come as a 0, this will come as a minus 168 and plus 0.168. And now you can see similar to earlier case, this is negative, so going anti-clockwise, this is positive, so going clockwise. So this is again pushing downward, so this is again it will be creating minus effect. So indeterminate displacement will come as a k ml square by ei, where m is this, m is equal to 0.168. Okay, so with that note we can go to this like n values, and we can get the k value. So similar to earlier problem, you will have to substitute n is equal to 1 where movement is applied, and from there you have to get the 5 intervals this side and 4 interval this side, and mid span it is at 0.5. so you will get n values as a 0, 0.2, 0.4, 0.5, 0.6, 0.8, 0.1, and on the other span it will be n is equal to 0.75, 0.5, 0.25, 0, and accordingly you can calculate the k. So earlier if it comes combine SF for BM and shear force and bending, and you don't have to repeat whichever is required again, so you can continue with that. And let us continue with those k values what we have earlier got, and we will use this determinate displacement and try to solve. So let me do again. So this is the determinate displacement for the bending moment. So total ILD will be nothing but EI in bracket determinate displacement plus indeterminate displacement. In this case, indeterminate displacement has come out as k ml square by ei, and indeterminate determinate displacements are this. So let us start with y naught. What is y naught? You can see here it is ei into 0 minus k is equal to 0, m is 0.168, we got this 0.168, and L is 5 square by ei, and this comes out to be 0. Okay, and now let us go to the second point. This we'll call it as a y1 ei in bracket. What is value of determinate displacement? 0.5 by ei minus what will be the k value. So k value in this case is 0.032, and m value is 0.168, and y is L is 5 by ei, and if you do this it will come as a 0.37. Similarly, if you do it for y2 will be here, that is 1 by ei. So ei in bracket 1 by ei minus 0, k for this location is 0.056, m is 1.168, L is 5 square by ei, and if you do this it will come as a 0.765. Then yc, so this is the critical location, that is maximum value, we'll call it as a yc is equal to ei in bracket. What is value at yc? 1.25 by ei minus 0, value of k for n is equal to 0.5, it will be 0.0625 into 0.168 into 5 square divided by ei, and this comes out to be 0.988. It has got reduced from 1.25 to 988. Then we'll go to this side now. Okay, this side, this point and this point. So y3 will be it will be this point, so it will be 1 ei in bracket 1.0 divided by ei minus for n is equal to 0.6, k is equal to 0.064 into m is equal to 0.168, 5 square divided by ei, and this value comes as 0.73. And then last one is y4, that is ei in bracket 0.5. This is determinate value is 0.5 by ei minus 0.048 into 0.168 into phi square divided by EI, and is equal to 0.298, and at the center point this is also 0, k is 0, so y5 will be EI in bracket 0 minus 0 is equal to 0. And you can note now for these y6, y7 and y8 and y9, determinate displacement is not 0. If we have been asked to find out the BM in this fan, you would have got this diagram, and you would have got this side 0 determinate displacement and this side non-zero determinate displacement. That difference you can note here. So here for next values, determinate displacement is 0, y6 is equal to 0 minus kml square. Now L in that side is L is 4 meter, you have to be careful, 0.0546 into 0.168 into 4 square divided by EI, so it will come as a 0.13. okay, this is negative, and then y7 is equal to EI, I forgot, EI in bracket 0 minus 0.625 into 0.168 into 4 square divided by EI, and this comes out as minus 0.157, and then y8 is equal to EI in bracket 0 minus 0.039 into 0.168 into 4 square divided by EI. This comes out to be minus 0.097, and y9 is equal to 0. So you have now you got all the values. Let us draw the ILD for indeterminate. So once again we will take the span, mark it at 1 meter, 1 meter, 2 meter, 3 meter, 4 meter and 5. So this is our AB beam, and then again 1 meter, 2 meter, 3 meter and 4 meter. This is our BC span, okay, and then at the mid span, this is our Z value. So you know, let us first draw the don't do this in exam, I'm just doing for the your understanding, and you can see this everything has been subtracted from the positive determinate values. That is when it was highest, let us say YC determinate was 1.25, indeterminate became around 1. So we will have to be in a concave curve, and it is obvious, so that other side it will become convex, so it will become concave curve, something like this. Sorry. And as this become concave curve, the other side it will become convex, because these are this side negative values, and then we will put these numbers here. So we got this is the ILD, forget about this dotted line. So these are the values. So if we put this, this comes out to be 0.37, 0.765, 0.988, then 0.73, 0.298, and this side 0.147, 0.168, and I'm sorry, this is 0.13 and 0.157, and this one is 0.097. That's it. Thank you.